Welcome to this technical presentation by Passive Plus Incorporated. This is the first in a series covering the specifications for multi-layer ceramic capacitors. My name is Bob Grossback and I'm an RF engineer with Passive Plus Incorporated. Multi-layer ceramic capacitors are found in virtually every piece of electronic equipment, ranging from cell phones and base stations to MRI machines, GPSs, radar, and satellites. The title of this presentation is Specs and Specmanship, and we're going to try and cover not just what specifications there are on MLCCs, but what they mean, how they're measured, how to interpret them, and here's where the specmanship term comes in, to what extent they reflect the actual performance of delivered products. Just to make sure we're all on the same page or on the same slide, this is an MLCC, and we see that it consists of a brick of ceramic with interleaved metallic electrodes, and with each end terminated on 5 sides by solderable terminations. One way to characterize MLCCs is by the firing temperature of the ceramic. The so-called high-fire ceramics are typically magnesium titanate, sinter at about 1300 to 1350 degrees C, and have refractory metal electrodes, for example, palladium. In contrast, the low-fire ceramics are typically made of barium titanate, sinter around 1000 degrees centigrade or even less, and that permits use of silver or silver alloy electrodes. And of course, the silver electrodes have a lower resistivity or resistance than the platinum electrodes or palladium electrodes would. The production process for MLCCs is really quite complex, and it often consists of 90 to 100 separate steps. We won't attempt here to cover them all, but the slide lists some of the principal processes. Basically, we begin with a ceramic powder that is mixed into a liquid and then deposited on a conveyor belt. The conveyor belt is maybe a foot or a foot and a half in width, and heated, and so it becomes a tape-like consistency. Electrodes are then deposited on the tape, and then squares are so-called spanked out of the tape, and the electrodes are oriented in alternating directions by a special machine designed for that purpose. Then these squares are dried, singulated, which means diced or cut up into actual capacitor sizes, sintered in ovens, and then the finishing operations are done, which consists of corner rounding and application of the terminations and final metallizations, generally solder of some type. We're going to focus here on this list of electrical and physical specifications for MLCCs. We start at the top with cap value. That should be a fairly straightforward one. Generally, we would assume that an engineer, for example, would know what capacitor value he wants. It would be specified typically in picofarads or nanofarads, and so there's not much else to say about that. Next comes the physical dimensions. This is somewhat more subtle. Basically, there's 2 classifications of physical dimensions. The EIA sizes, typically 0402, 0603, 0805. Those mean 0402 is 40 mils long by 20 mils wide, 0603 60 mils long by 30 mils wide, etc. And then the more or less square-shaped series, which are typically 55 mils squares, 110 mil squares, 250 mil squares, 380 mil squares, so that's a different series. The physical dimensions that one would choose are related to the other specifications, so there's no absolute rule. If one needs a higher voltage, one might need to choose a physically bigger part. If one is concerned about parasitics or resonances, one might have to match the physical size of the part to the transmission line. Let's now consider the third spec on the list, which is the tolerance. Tolerance itself is actually a very straightforward specification and easy to understand, but the distribution of the capacitor values within that tolerance may be less so. One might ask, why is that distribution important? Well, imagine if you were designing a filter of having 4 or 5 capacitors. Imagine if they all the values piled up at one edge of their tolerance, let's say all the highest tolerance part. The filter may turn out to be out of spec. Hopefully they won't all be that way. So what one does to determine the yield to a spec is generally called a Monte Carlo analysis, and this is available on a number of simulators. And that selects randomly values within the tolerance limits and assigns them to the components, and one can see what the yield of the total circuit that you're building is to a given spec. If you're having a 90% yield, for example, you have to account in pricing the part for the fact that you may be throwing 10% of them away or reworking 10%. If you turn out to have a 50% yield, it may be that you really have no design and you have to go back and begin ordering tighter tolerances. So it's very important to do this kind of analysis, and to do it properly, you need to understand what the distribution is within the tolerances. So this first slide shows a kind of idealized situation. You order the tightest tolerance. Ideally you'd expect a normal or Gaussian distribution centered on the nominal value, and you get a truncated distribution that looks like this. In practice, you almost never hit exactly the nominal value because there's variations typically in the dielectric constant of a given lot. There's variations, even the 1/10 of a mil tolerance on the tape sounds very tight, but when you consider that tapes range in thickness typically from 1 to 4 mils, 1/10 of a mil out of 2 mils is 5% right there. So most of the time you get a little offset on the nominal value, and that gives you a plot that's not quite like the ideal truncated Gaussian, but still not too terrible when you order the tightest tolerance. What happens now if you do not order the tightest tolerance? Then you get something that may look like these two slides. What you might naively expect is that you would get something in this top picture here that's an offset Gaussian varying between your two somewhat looser tolerances. We've selected 5% here as an example. But in fact, what you get in practice is something with a big notch taken out of it. And the notch is for all those people who did spend the money, the additional money, to order the 2% and the 1% parts. You do not get them. You get parts between 2 and 5% and -2 and -5%. So what you end up with is this kind of bimodal, so-called bimodal distribution, which is quite different from what you might naively expect. A third case, perhaps even worse, is when an adjacent nominal value, the tail end of that distribution falls within your tolerance band, and that muddies things even worse as far as the distribution. Also shown are certain measurement guard bands. They're generally small compared to the tolerance range, but there you have the uncertainty of the measuring instrument as well, and good manufacturers always make sure that to select something that makes sure that the customer gets his tolerance value, and so you leave room for this measurement error. The takeaway from all of this is in calculating Monte Carlo yields, particularly when you're not using the tightest tolerance parts, you won't get realistic results unless you account for the issues that we've noted, and particularly unless you can simulate some kind of bimodal distribution. Let's move on now to our next specification, ESR, or equivalent series resistance. The top schematic shows a generally accepted equivalent circuit for a capacitor, indicating both dielectric losses and metallic losses. Dielectric losses result from the loss tangent of the dielectric. We typically approximate what that is by measuring at the dissipation factor at 1 megahertz for cap values under 1,000 puff, and 1 kilohertz for cap values greater than 1,000 puff. And So in this range, at 1 megahertz to 1 kilohertz, the loss is almost surely all dielectric, and so we have an approximation to the loss tangent. The other form of loss is metallic loss, and that is dependent on the number of electrodes, as shown, frequency, resistivity, electrode aspect ratio, length to width ratio, that means the skin effect, and the proximity effect. All these latter effects and the frequency effects are really all part of a skin effect. What happens is that current is excluded from the middle of the electrode bundle and accumulates or concentrates near the top electrode and bottom electrode and along the sides of the individual electrodes. Here in general is the way ESR varies with frequency. At low frequencies, dielectric loss is seen to dominate. At higher frequencies, metallic loss is seen to dominate. And there's a large middle region where both contribute about equally to the total ESR. In terms of what you might buy from Passive Plus Incorporated, our N series has a lower metallic loss because it has silver electrodes, so that those would be applicable for ESR at higher frequencies. The P or C series has a lower dielectric loss. Those would be better to use at the lower frequencies. And we're now going to kind of give you an indication of what higher and lower might be in this context. So this slide shows the actual measured ESRs of a couple of different capacitors, same value but different series. The N series again has a low metallic loss, C series has the better or lower dielectric loss. And we see here, for example, that for the 10 puff parts that there is a crossover at 90 megahertz, meaning that above 90 megahertz, the 1111N would have a lower ESR. Below 90 megahertz, if that's where you were working, the 1111C would have a lower ESR. The 6.8 puff value has a crossover at 180 megahertz. Next slide shows these same kind of, these are experimental measured curves for 33 puff and 100 puff capacitors, and there we see that the crossovers are respectively 95 megahertz and 40 megahertz. Generally, it's true that the higher the cap value, the lower the crossover frequency, and of course vice versa, but it's not an absolute rule because differences in electrode pattern and the number of electrodes also have an effect. So it's a generalization but not an absolute one. For us to have really confidence in a specification, it helps to understand how it's measured. Consider that ESRs for these multi-layer ceramic capacitors typically range from 10 to several hundred milliohms and appear in series with capacitive reactances that could be in the hundreds of ohms. So you get enormously high Q values, and as a result, common measuring and convenient measuring instruments such as vector network analyzers or impedance analyzers are simply not sufficiently accurate under these conditions. So most MLCC vendors use a resonant transmission line to make this measurement, and this is what's shown above. This particular one was made by the Boonton Corporation, which kind of became an industry standard to perform ESR measurements. Unfortunately, Boonton is discontinued this series several years ago, so they're no longer readily commercially available. The measurement theory, and as well as the practice, is actually fairly involved and complex. First, a calibration is done so that the line is open circuited, the transmission line is open circuited, and the Q versus frequency is measured. The line is then short circuited and the Q versus frequency is measured. And finally, the unit under test is inserted. There's a plunger that squeezes the capacitor up against the center conductor of the coaxial resonator. It's assumed in all these measurements that the capacitor can be represented by a simple series RLC circuit, and of course, under circumstances we're going to discuss, this is open to some question. You can see the equations here that are used in the extraction of the ESR. They're not simple. and the whole calibration procedure is not, and measurement procedure is not simple, and so there's a fair amount of room for errors. Here is how the Q factors look graphically. All these plots are Q versus frequency on the horizontal axis. The top the axes are logarithmic. The top plot is the open-circuited coaxial line. Next is the short-circuited line. You see that has a lower Q. The reason is the contact resistance of the short is not a perfect resistance, and in fact varies with frequency, and it's this procedure that enables you to de-embed it and remove it from the final ESR measurement. The measurement of the unit under test, when that is inserted, that's shown in the third plot here. It has the lowest Q, and there's various other correction factors that go into making an actual measurement. So there are several issues or errors that arise from these kinds of measurements. Unfortunately, in the original Boonton description of manual, they mention a way to remove what they call excess inductance from the capacitor. This results from a change in the cross-section of the coaxial line. It's generally bigger. The center conductor is larger than the capacitor on the test, and you know that a short section of smaller conductor coaxial line has a high impedance coaxial line, contributes inductance, which you don't want to really attribute to the capacitor. So there's a procedure to remove that involves calculating the free space inductance of a capacitor. Unfortunately, a term was omitted. The expression was truncated in the Boonton manual. As a result, if you use it literally on cases that are square and squat in length, or almost cubical, you come out with a negative inductance value, which is clearly impossible. So there are errors there, and there's an error in the actual procedure of how to do that. Other errors that result from some features of the derivation that are simply never quite made it to the two standards that are available for this, which is the EIA standard, the Electronic Industry Association standard, and the ASTM standard. And those include the coaxial plunger reactance and the actual inductance, which, if you would look back at the slide with the equations, you'd see there is a term that involves there is some energy stored and dissipated in the inductance. That's not included in the final expression given in the standards. And this bottom one, stray capacitance, we're going to go into that in the next slide a little bit more carefully, but the bottom line is that you can get very large ESR measurement errors for low value capacitors that have small case sizes. Let's take a look at this so-called stray capacitance error, because that's perhaps the one that's easiest to immediately apprehend. If you take a low value capacitor and you put it into the measurement system, you will have stray or fringing or shunt capacitance in parallel with it, caused by the proximity of the center conductor of the coax to the end face of the plunger. This is essentially a lossless capacitance, and so it gives you unreasonably optimistic results for the ESR. There is a correction available, again, even in the Boonton manual, but it never quite made it into either of the standards available. So what you have, again, the greatest errors are for low value capacitance, typically less than 2 puff, and small physical size. That's what maximizes the fringing. And what you have are errors that can be in the hundreds of percents. So you may ask yourself, why hasn't this has been recognized before, it's been around, why hasn't it been corrected and rolled into the standards? One possibility is that no individual company is going to do it because it would make their product look like it had a higher ESR than the competitors. So the only way it could be done is through the standards committees, and no one has quite gotten around to actually implementing it yet. So here's some things to remember when comparing ESR specifications from different manufacturers. Usually these are given as typical anyway, whatever that means. But there are a number of ambiguities, measurement inaccuracies we mentioned. There's the lot-to-lot differences, and within lot differences, we don't know if the word typical, what exactly it applies to. And there are various design trade-offs, so that sometimes a manufacturer may be trading off of voltage withstanding capability, or heating, or economics with ESR, give you a less expensive part. One way, for example, to optimize ESR is to use within a series different dielectrics and different electrode patterns. This can be done, but it's usually quite expensive to do compared to single pattern and single dielectric. So you have these trade-offs that different manufacturers use, and it's important in comparing to see what you're getting and what you're giving up. So this concludes our discussion of the first 4 MLCC specifications. The next part of this series will take up series and parallel resonances, termination metalizations, and voltage breakdown. Again, I'm Bob Grossbach. The company is Passive Plus, and thanks for your time.